Welcome back to my rubber heart. Today we are talking about one of the simplest yet most incredibly versatile polymers in the world, polyethylene. Now I know, when people think of polyethylene, the first thing that comes to mind is probably plastic bags or bottles, maybe even food packaging. But polyethylene is so much more than just a commodity plastic. In fact, its versatility is one of the most fascinating qualities. Depending on how it's processed or modified, it can act like a rigid thermoplastic, a soft elastomer, or even a durable thermoset. It's used in everything from wire insulation to roofing membranes to synthetic rubber blends. And today we are going to break down how and why that's possible. At its core, polyethylene is a very simple polymer. It's made up of repeating units of ethylene, giving it a long chain of carbon atoms with hydrogen atoms hanging off the sides. That simplicity gives it a certain purity of behavior. It's chemically resistant, has low friction, good flexibility, and, depending on its molecular weight and branching, it can range from soft and waxy to tough and rigid. As a standalone thermoplastic, polyethylene comes in several grades: low density or LDPE, linear low density or LLDPE, high density or HDPE, and even ultra high molecular weight or UHMWPE. Each type behaves differently depending on how the polymer chains are arranged and how densely they are packed. LDPE is soft, flexible, and easy to process, while HDPE is stiff, strong, and more crystalline. These materials are widely used in films, containers, pipes, and packaging. But polyethylene doesn't stop at being just a commodity plastic. It can be compounded into high-performance thermoplastic compounds by blending it with fillers, UV stabilizers, flame retardants, or impact modifiers. This allows it to be customized for technical applications like geomembranes, cable sheathing, or automotive components. And the story gets even more interesting when we talk about cross-linked polyethylene, or XLPE. By cross-linking the polymer chains, we essentially transform polyethylene from a thermoplastic into a thermoset. That means it no longer melts when heated. It becomes a permanently set material with improved thermal stability, chemical resistance, and mechanical strength. There are several ways to cross-link polyethylene. One common method is peroxide cross-linking, also known as the DCP method. In this process, a peroxide like dichroyl peroxide is mixed into the polyethylene and, when heated, decomposes to form free radicals. These radicals attack the polyethylene chains and create crosslinks between them. This technique is widely used in wire and cable insulation, where heat resistance and electrical insulation are critical. Another technique is silane grafting, or the cyoplast and monosil processes. Here, silane molecules are grafted onto the polyethylene backbone, often using vinyl trimethoxysilane. When exposed to moisture, these silane groups react to form siloxane bridges, creating a crosslink network. This method allows the crosslinking to occur during or after processing, which is particularly useful in extrusion applications like plumbing, pipes, and tubing. There's also radiation cross-linking, where polyethylene is exposed to high-energy electron beams or gamma rays. The radiation induces free radicals along the polymer backbone, which then cross-link. This method is used in heat shrink tubing, medical devices, and specialty films. What is interesting about radiation cross-linking is that it doesn't require chemical additives. It happens purely through physical energy, and the degree of cross-linking can be controlled very precisely. But polyethylene's versatility doesn't end with cross-linking. One of its most intriguing modifications is chlorinated polyethylene, or CPE. This is polyethylene that has been chemically modified by substituting hydrogen atoms along the chain with chlorine atoms. The chlorine increases the polarity of the polymer, making it more flame retardant, oil resistant, and compatible with other polar materials. Now, what makes CPE so fascinating is that it can behave like a rubber, a true elastomer. It can be compounded with fillers, plasticizers, and curatives, and then cross-linked using either peroxide or sulfur-based systems, much like traditional rubbers. Chlorinated polyethylene is used in a wide variety of rubber-like applications: weather-resistant roofing membranes, wire jackets, flexible hoses, industrial gaskets, and even in blends with other rubbers like CR or EPDM to improve low temperature flexibility or oil resistance. And because it has built-in flame retardancy due to the chlorine content, it often meets strict safety codes without requiring additional additives. That gives it a huge edge in applications like cable sheathing and automotive seals, where fire safety is a concern. Beyond that, there are even more specialty modifications of polyethylene. You've got metallocene catalyzed polyethylenes, which have extremely uniform molecular weight distribution and offer improved clarity, sealability, and impact strength. These are especially useful in packaging films and medical applications. Then there are graft copolymers, where polyethylene is chemically bonded with polar groups or other polymers to enhance adhesion, improve blending with other materials, or provide reactive sites for further modification. All of this really goes to show just how broad the design space is when you are working with polyethylene. It's not just a basic plastic, it's a platform material. You can keep it simple for cost-sensitive applications or push it into high-performance territory with just the right processing, additives, or chemical modifications. Whether you need a rigid part, a soft film, a cross-linked pipe, or a rubbery gasket, polyethylene has a pathway to get you there. Thanks for joining me today on my Rubber Heart. I hope this episode helped you see polyethylene in a new light, not just as a basic thermoplastic, but as a truly versatile and adaptable polymer. If you like this breakdown, make sure to subscribe and drop a comment. Let me know what polymer you want to explore next. See you next time.